Hello students, my name is Charu Ma'am. I have done MTech in Information Security from NIT Jalandhar. I have more than 3 years of teaching experience and I have qualified GATE. So in the last lecture we have talked about the different memory management techniques. We talked about the contiguous memory allocation method, non-contiguous memory allocation. So I have just given you the overview of the two techniques. Let's study in detail about the two methods. First, we'll talk about the contiguous memory allocation method. So under that, we are going to study the fixed partitioning scheme and variable partitioning scheme. So see here, in the fixed partitioning scheme, what we have, memory will be divided into the fixed number of partitions. And in one partition, only one process can be accommodated. Like here, we have 4 memory blocks, and here we have different size of blocks are there, but the size is fixed like this. 4 MB I have given to the first memory block, 8 MB, then 8 MB followed by 16 MB. Suppose I have 4 processes, P1, P2, P3 and P4. I want to execute 4 processes and each is having some size. Suppose 3 MB size is having 7 MB, P3 is also having 7 MB and P4 is having 14 MB size. Okay, so let me place these processes in using fixed partitioning scheme. First I will place in here. So here I am going to place the first process, that is P1 is placed here. How much memory is left? 1 MB. If 3 MB process is allocated to first block, 1 MB space is left. Then P2 came, it is allocated in the second memory block because it can't be accommodated in the first memory block. And what is the size remaining? If 7 MB is allocated, 1 MB. Then again P3 of 7 MB came, it is allocated here, P3, because it can't be accommodated in the first two blocks. So here how much size is left? 1 MB. If 7 MB is allocated, last one is 14 MB. 14 MB will be accommodated in the last block. P4 will be accommodated in the last block. And how much size is left? 2 MB. If I subtract 16 minus 14, that is 2 MB. So how much the total space left? Total unused space will be 1 plus 1 plus 1 plus 2. How much it is? 3, 4, 5. So total 5 MB space is left. Suppose there is a scenario if after P4, P5 of size 5 MB comes. Suppose after P4, P5 came of size 5 MB. So we know that 5 MB space is left. Yes, 5 MB space is left here. Here some space is left. Here some space is left, and here. So total 5 MB space is left. But I can't accommodate the process P5 of size 5 MB because it is not available in the contiguous manner. It is not available in the contiguous manner. So I can't accommodate P5 here. I can't accommodate P5 here. So this process is called as external fragmentation. This process is called as external fragmentation. So there are some cons of the fixed partitioning scheme. First is internal fragmentation. Second one is external fragmentation, then process size limitation, then degree of multi-programming is less. Okay, so what is this internal fragmentation? It is if size of the process, if size of the process is lesser than total size of the partition, then some then some size of partition is wasted or unused. External fragmentation I have explained here with the help of example. Process size limitation. So there is size limitation is there because initially we divide the memory into fixed partition blocks. So if the process of bigger size came, so we can't accommodate it. So there is limitation on the process size. Next is so obviously the degree of multi-programming will be less if there is process size limitation. I hope this is clear. Fixed partitioning scheme. Next one is the variable partitioning scheme. So initially the RAM is empty. The partitions are made during the runtime. It is very important. The partitions are made during the runtime according to the process requirements instead of partitioning during the system configuration. Okay, so here the partitions are done according to the size of the process. Suppose I'm having 4 processes P1, P2, P3 and P4. P1 is having size 2 MB, then P2 is having 7 MB, P3 1 MB, P4 5 MB. Okay, so according to the size of process, this memory will be divided. Okay, so the size of partition will be equal to the incoming processes. That's how these partitions are made. The partition size varies according to the need of process, so internal fragmentation can be avoided and efficient utilization of RAM can be done. See here, there is no chance of internal fragmentation. Why? Because size of partition will be equal to the incoming processes. So there is no chance of internal fragmentation. Okay. So P1 is placed here, P2 is here, P3 is here and P4 is here. Now let us suppose P1 and P3 executed completely. Suppose they are executed completely. Now how much space is left? P1 is having 2 MB size plus P3 is having 1 MB size. Okay. So total 3 MB is free now. Okay. So suppose now P5 of size 3 MB comes. Okay. So now this is free. Which space is free? This is free and this is free. Right. Now in spite of P1 2 MB, 1 MB, total 3 MB is available, but it can't accommodate. Now it will not be able to load in the memory. Why? Because here also the here the partition is not available of that particular size in the contiguous manner. Okay, so the size is not available in the contiguous manner. That's why we can't accommodate P5 here. So what it will be? It will be of scenario external fragmentation. So still external fragmentation is there in the variable partitioning scheme. So next disadvantage is it is having complex implementation. Okay, but here in the variable partitioning scheme, what we do is we can do the compaction. This problem can be solved with the help of compaction. What is this compaction? Compaction is moving all the processes towards bottom or up to make free available space in the single contiguous manner. हम ये वाले प्रोसेसेस को बॉटम पे मूव कर सकते हैं जो एग्जीक्यूट हुए हैं, और या तो टॉप पे. तो क्या होगा कि एक ही जगह पे कॉन्टिग्यूस मैनर में we will be having free space available. But compaction is undesirable. Okay, because it is very costly procedure. So it is undesirable. So implementation becomes very complex. We can't do it in, so it interrupts all the running processes in the memory. So it is undesirable condition. Next one is the partitioned allocation methods. Next one is the partition allocation methods. So here we have, in this method, the memory is divided into different blocks, partitions. Each process is allocated according to the need. Okay, so we have different placement algorithms here. First one is first fit, second best fit, third is worst fit. Okay, so in the first fit, what is there? In the first fit, uh, the partition is allocated. In the first fit, partition is allocated to the first sufficient block from the top of the memory. Okay, so this is your first fit. Best fit is allocate process. It is allocate the process to partition the partition that is which is sufficient partition, means that is first sufficient partition freely available in the memory. Okay, and third is worst fit. So here we allocate process to the partition which is largest among all freely available space in the memory. Okay, so let us understand these different placement algorithms with the help of example. So here consider request from the processes is given in the order 300k, 25k, 125k and 50k. This is the order of the processes. Let there be two blocks of the memory. There is two blocks of the memory of size 150k followed by the block size 350k. And which is the following partition allocation schemes can satisfy the above request. Okay, first option is given best fit or not, but not the first fit. So we have to see which satisfies the best. Okay, whether it is first fit or the best fit. Let us see the scenario. Let us see for best fit. So what best fit says, allocate the process to first partition that is able to accommodate the process. Okay, suppose I am having this memory block. This is of size 150k and this is of size 350k. Okay, So the processes are 300K, then 25K, then 125K, followed by 50K. This is the order of the processes. So according to the best fit, 300K, it can't be accommodated in the first block. Second block, it can accommodate. Okay. So I will assign here. So here I will assign this 300K is assigned. How much space is available? 50K. Okay, this is done. 25K. So 25K can be accommodated here. So I will accommodate here. So here I will accommodate 25K. How much is left? Still 25K is left. Okay. So 125K. When 125K came, I will accommodate it in the first block. And how much is left? 25K. So what about 50K? Here how much space is available? This is available and this is available. Can I accommodate here? This is 25K. This is 25K. But I can't accommodate here because it is not available in the contiguous manner. So 50K can't load into the, it will not be able to load the in the memory. Let us see the scenario of the first fit. Let us see what happens in the first fit. I have the memory block. Memory block is divided into two parts. First is 150K, next is 350K. Here also request came in the order 300K, 25K, 125K, then 50K. So first process came. I will accommodate here 300, 300 will be accommodated here. How much is left? 25K. Next 25K comes. First fit means first available space I will allocate the process there. So here first available space is here in the first block. I will simply allocate 25K here. Okay. So it is also executed. So next one is how much space is left? 125K is left here in this block. Then 125 will be accommodated here. Yes, it can be accommodated here. So 125K is accommodated. Next 50K. So here, sorry, here 50K is left. So this 50K will be allocated in the last block. This is also executed because here 300 is there. So left space is 50. So 50 is there. So it is the first fit accommodated all the process in the memory. Okay. So this is the best allocation method in case of this scenario. So it can depend upon the available request from the processes or available partitions. So it depends. So in this case, what is the answer? First fit is best but not the best fit. Okay. So it depends upon the scenario which one is better. So you can solve like this. Hope this is clear to you. This partitioned allocation methods. Next one is paging. This is very important topic, paging. So paging technique. So in this method, in which the processes are retrieved from the secondary memory into the main memory in form of pages. Each process is divided into pages and main memory is also divided in form of frames. Main memory is divided into frames, and one page is stored in one of the frame of the memory, and the pages can be stored at different locations of the memory. And see here what happens here. First you need to know is, in paging, the frame size should be equals to page size. Okay, the frame size should be equals to page size. So what happens here? CPU generates some logical address. This one is the logical address. This is the physical address. Okay. P plus D. D is the offset here. D is the offset here. So P is the page number, F is the frame number, P is the page number, and F is the frame number. Okay. So page number plus offset makes the logical address. Physical address will be obtained with the help of frame number and offset. Okay, let's take this scenario where your physical address is 12 bits and logical address is 13 bits. Okay, so let us see how the paging will be implemented here. So see here, the physical address that is founded in the memory and the logical address, that is the virtual address also, and that is the address generated by the CPU. And mapping from virtual to physical address is done by the memory management unit. The mapping of virtual address to the physical address is done by memory management unit, that is called as paging. And this is called as page map table. Okay, that contains the page number and corresponding frame number. Okay, so that is your page table, or you can say that page map table. And one thing you have to remember here is your every process has its own page table. Every process is having its own page table. Okay, suppose here I am having the physical address. Physical address is 12 bits, logical address is 13 bits, and I'm able to find out the physical address space. Okay, that is of 2 raised to power 12, and here I will be able to find out logical address space, that is 2 raised to power 30. Okay, if I have to find the number of pages, okay, so that will be find it out by logical address space divided by page size. Okay, so let us suppose here page size is given as 1k words. Suppose the page size is given as 1k words. So what will be the LAS? 2 raised to power 13 over 1k is 2 raised to power 10. So what it will be? 2 raised to power 3. So from here I will be able to get the page number, that is P equals to 3. How to find the number of frames here? Number of frames will be equals to physical address space by the page size. What is your PS here? PS is 2 raised to power 12 divided by frame size. I told you that your page size equals to frame size. So what it will be, 2 raised to power 12 divided by 2 raised to power 10. Same hai, 2 raised to power 2. From here you are getting the f, that is frame number 2. 2. Okay. So I will put here, what is the value of p here? 3. And this total LA value is given, logical address 13 bits. And here this value is given as physical address as 12 bits. Okay. So if it is 13 minus 3, I can find the offset. That is, how much it is? It will be 10 in this case. Here also 12 minus 2, f value we know 2. 12 minus 2 is 10. D is 10 here. Okay. So what happens? CPU will generate the logical address. From there we will get the value of page number, which page number we have to assess. Now in this case page number is 3. Page number 3 will be assessed. Okay. So that will go to page number, suppose here it is so let us say here P3, I found the P3. So P3 is here. So I find it out the page P3. I will find the corresponding frame number with the help of page map table. What I get? F2, frame number 2. I will go here. Here I will refer to frame number 2 in the physical memory. There I get the, suppose here process 3 is there. Okay. So this is P3 that is placed in the frame number 2. Okay. So like this we have to find. यहाँ पे first CPU will generate the logical address, then page number will be find it out, page number will be assessed with the help of page map table. There we get the value of frame number. We'll go there, we will find the physical memory, their frame number. I will refer to that particular frame number, and that particular frame number contains the particular page. Then here the CPU will execute that particular page by finding out with the help of this process. I hope it is clear to you. Okay, let's practice some numericals based on the paging. Let me, okay. So here, first numerical is, consider a system with logical address of 27 bits, physical address of 21 bits, page size is given 4K words. So it is asked that find out the number of pages and number of frames. Let us write this PD if I am talking about logical address, and this is FD if I am talking about physical address. What is the value of logical address? It is given 27 bits. And what is physical address? It is given as 21. Okay. So let me write. So if page size is given to you, page size is given, okay. So from page size 4K words. So I can find out the offset. Okay. So it is 2 raised to power 2 into 2 raised to power 10. How much it is? 2 raised to power 12. So from here I can find out the offset. This is also the another way I can find out the offset. D is 12. So from here I can write D is 12. Here also D is 12. 21 minus 12 is 9. Okay. And 27 minus 12 is 15. So I have find it out. So page number is 15. Number of pages will be equals to 2 raised to power 15, and number of frames will be equals to 2 raised to power 9. Which one is the correct option? First one. Number of pages is 2 raised to power 15 and number of frames are 2 raised to power 9. This is how you can find out the number of frames and number of pages. Simple है. Second question is, consider a system with byte addressable memory and physical address space of 64 MB, 32-bit logical addresses and 4 KB page size. You have to find out the size of the page table in the system in megabytes. Options are given. You have to take the correct option. So let us see the scenario, how we can find out. So page size given है. Page size is given. How much it is? 4 KB. 2 raised to power 2. K is 2 raised to power 10. Total 2 raised to power 12. From here we get the value of offset, that is D as 12. Right. Next we have to find out what is given. Physical address space is given, that is PAS. It is given 64 MB. Okay. What it is? 2 raised to power 6 into 2 raised to power 20. M is 2 raised to power 20. So how much it is? 2 raised to power 26. So what is the value of physical address? It is 26 bits. I'm talking about. Okay. So from here, if this is physical address, I can take it as 26 bits. It is frame number, this is offset. And we have calculated the offset, this is 12. What will be your frame number? 26 minus 12 is 14 bits. This we get, right? So next we have to calculate the number of frames in the memory. Number of frames in the memory, we have find it out, that is 14, right? We have find it out, 14. Okay. Next one is we have to find the process size. Process size. So number of bits in the logical address. How much LA is given? That is 32 bits. Okay, the process size will be given by 2 raised to power 32. So how I will write it, like 4 2 raised to power 2 into 2 raised to power 30, that is GB. So I can write the process size as 4 GB. So what is the value of number of entries in the page table? How much it is? It will be equals to process size divided by page size. Process size divided by page size. What is the size of process? 4 GB, and page size is given as 4 KB. 4 KB. Okay. So it will be 2 raised to power is 30. 2 raised to power 2 into 2 raised to power 30. Here 2 raised to power 2 into 2 raised to power 10. So it will be somewhere 2 raised to power, this will get cancelled out, 2 raised to power 20 page entries will be there. Okay. So next we have to find out the page table size. Size of page table will be given by number of page table entries multiply by the page table entry size. Page table entry size. Okay. So this will comes out to be 2 raised to power 20. We have find it out here, right? Into how many, what is the page table entry size? That is the number of bits in the frame number. कितने number of bits है frame number में? 14. So it will be 14. But now see in the options, I can't write 14 in the power of 2, but it is somewhere, it is given in megabytes, this values. So I can take 14 as somewhere nearest to the power of 2. 16 I can take approx. Okay, if I take it as approximate 16, so what it will be, 2 raised to power 20 into 2 raised to power 4. It will be 2 raised to power 24. So what it will be? It will be 2 raised to power 20 into 2 raised to power 4. So what it will be? It will be around 20 into 2 raised to power. So if I have to convert this bits into bytes, because the answer is in bytes, so it will be 2 raised to power 2. So it will be 2. So yeah, it will be 2 megabytes. So this is in bits, this is in bytes. So the answer will be 2 mega is the correct option. I hope this is clear to you. Let us try another GATE question. So this is, consider a computer system with 40-bit virtual addressing and page size of 16 kilobytes. If the computer has a one-level page table per process and each page table entry requires 48 bits, then the size of the per process page table is, you have to calculate in MB. So this was asked in the numerical answer type. I have given the here options, but in the GATE question, no options are there. So you have to just type numerically the answer. You can pause the video and you can try this numerical by yourself. You can pause it and you can try it. Otherwise, you can see the solution after trying. But first you try to solve the question with yourself. Okay. Okay. Let me provide you the solution for this one. So size of the memory is given. Size of the memory is given. What is the size of memory? 40 bits it is given. So I can write it as 2 raised to power 40. What is the size of page? Page size is given 16 KB. Okay. So 2 raised to power 4 into 2 raised to power 10 is 2 raised to power 40. First I can find the number of pages here. Number of pages can we find it out? How it can be find it out? The size of memory divided by the page size, that is 2 raised to power 40. What is 2 raised to power 26? Okay, now I have to find out the page table size. Okay, page table size is given by number of entries in the page table into page table entry size, or you can say that number of bits you have used in the frame number. Okay. The number of page table entries, each entry is 48 bits. Okay, 2 raised to power 26. Okay, number of entries multiply by 48 bits, but we have to get it in bytes because we want the answer in bytes. So 2 raised to power 26 into divided by 8, it will be 6 bytes. Okay, so it will be 2 raised to power 6 into 6 into 2 raised to power 20. So when you multiply this will comes out to be 384 MB. M for 2 raised to power 20. 2 raised to power 20 is 1m. So the answer is 384. I hope the paging is clear to you. You can practice more questions and you can email me if you have any doubt. The email ID is provided to you in the video. So you can go there, you can ask the doubts, you can comment below also. If you have any doubts, I can reply there. Thank you.